Okay. So today we'll discuss the special cases of VCR. VCR stands for vapor, compression, refrigeration. So to understand the special cases of VCR, we need to understand the first flow diagram. Okay, the flow diagram of VCR, how it works. So it consists of four major components, what we discussed in the previous class. One is cabin. Cabin is also called evaporator, and it is at low temperature. Okay, keep in mind it is at low temperature. A condenser is at high temperature. Heat is rejected at high temperature. Next, and the second component is compressor. Important one is compressor. Next, third component is condenser. Condenser will be always at high temperature. And the fourth component, this one is expansion valve. Okay, expansion valve, or it is also called as throttling valve. Okay, and arrow mark is anti-clockwise. Okay, so this is working of VCR. So I will not take much time in explaining this quantity. I will go to the first case, case number 1. So there are three cases will come into the picture. One is, okay, are you students, am I audible or not? Because some students, they are saying that it is not audible. I hope it is audible for everybody. Okay. The first case is, always you need to remember the point, input to the compressor. Okay. There are three conditions of fluid we have studied. One is fluid. Another one is condition is wet steam. One more is dry, or last one is superheated steam. Okay. These are the 4 points. So to understand this, I will draw one simple TS diagram here. It is important. TS diagram, there will be two lines. One is saturated liquid line, another one is saturated vapor line. If your points lies on this line, you will call it as liquid condition. If your point lies on this condition, we will call it as dry condition. If your point lies somewhere here, right hand side of this vapor line, it is called as superheated condition. If your point lies between this curve and this curve, that point will call it as wet condition. Okay. What you may special cases is, in the given numerical, he will give the condition of vapor refrigerant at inlet of the compressor. Very important point. Please listen carefully here. The condition of this refrigerant at inlet of the compressor, whether it is wet or dry or fluid, this is the condition he will give. Okay, almost cases, the condition of the refrigerant at inlet of the compressor, that is at point number 1, maybe it is at wet or maybe dry. Out of these two, he has to give any one condition. Must and should, he should give this condition. Okay. If he has not given inlet condition, and there will be chances of giving outlet condition. Point number 2 means end of compression, whether the refrigerant is dry, whether the refrigerant is wet, whether the refrigerant is in superheated state. Out of 3, you must give any one compulsory. If not, it will be very difficult to solve these numericals. Okay. Now I will assume first case. What is the first case is, the input of the refrigerant at inlet of the compressor is, I will assume it is wet. What is my condition? Case number 1. The case number 1 is, I will write here, the refrigerant at inlet of compressor is wet. Means point number 1 is in wet condition. or else what will give second, the refrigerant at outlet of compressor. You must give any one case. Here it is given wet. Let us take outlet of compressor is also wet. Then how to draw the TS diagram and pH diagram for this condition? Assume this is a condition he has given in the numerical. Okay, any one case will be given. It will be very difficult to with all three cases. All three cases is not possible. Only one case is possible. Assume this condition is given in the numerical. So how to plot the TS diagram first? Temperature versus entropy. This is saturated liquid line, saturated vapor line. If the point lies here, you will call it as liquid state. If the point lies here, you will call it as dry state. If the point lies right hand side of this curve, this area, you will call it as superheated state. If the point lies between these two, we will call it as wet state. Now, what is the case number one? The refrigerant R12 or whatever may be at inlet of compressor is wet. Means point number one should be on in the wet region. So where should we consider? I will consider at this point. Wherever you can consider here, but always compression will be on the right hand side. So point number one is here. Now, what type of compression in the refrigeration? It is isentropic compression. So always we have to draw one vertical line. So point number one is beginning of compression in the compressor component. That is in the first place. Here I have written here. So point number one is input to the compressor. So compression. And point number two is outlet of compressor. Okay, what is the first case he has given? Case number one is the refrigerant condition at inlet of the compressor is wet. So that is the reason I have taken here. And if this case is not given, you will change the words. The refrigerant at outlet of the compressor is also wet. So point number should be here in the wet condition only. Sir, you can ask a question. Sir, why you are not plotting TS diagram like this? Why you are not taking here? Okay, here if you take here like this, where you will show the condenser part? Because the compression should be on the right hand side. Okay, next part 1 to 2. Next part is condenser. Condenser is always just constant temperature. Like this, you have to touch to this point. This is point 3. Next point 3, 4 is same. Nothing change. The remaining 3 processes will be remain same. For example, the 2 to 3 is condenser. Okay, 2 to 3 is condenser point. He may give the condition like the refrigerant outlet of the condenser, if it is wet, again I have to stop at this point only. What is the condition? If the refrigerant at outlet of condenser is wet, where should I stop? I should stop here only because it is wet. Up to here it is wet. Otherwise, he will use a condition that the condition of the refrigerant at outlet of the condenser is liquid. Then I have to stop here. But 90% they will not give the condition with respect to condenser. You will give condition with respect to compressor only. Okay, this is first case. I will use a second case. Okay, do not worry. If you not understood the first case also, try to understand second so that you will understand first easily. No issues. Second case. What is the condition? Condition of refrigerant at inlet of compressor is wet and outlet is dry. Okay, outlet is dry and inlet is wet. 90% any one condition will be given, my dear students. We will say only inlet or outlet. If the condition at inlet is wet, 100% at the outlet it should be dry. Okay, I will draw this diagram here. Okay, now condition of refrigerant at inlet of compressor. Inlet of compressor is, that is 1 to 2. I have to represent the process like this. This is 1 to 2 compression process. Is wet. Inlet of the compressor is point number 1. It is wet he is using. So wet means I have to take on in between these two curves. Somewhere you locate here on the right hand side of the curve. Locate here and make it point number 1. And what is the, when it is at condition at inlet to the compressor is wet, of course, if you draw one vertical and exactly straight line, it will reach to this curve. You stop here. Okay, this is point number 1 to 2. So point number 2 is on vapor line. You have to draw in such a way that, let me do it. I will erase this and I will draw once again, so you will that understand easily. Okay, so this is vapor line, this is liquid line. Now I am plotting. Compressor is at wet, so here is wet, point number 1, and outlet is dry. I have to draw like this. So point number 2 should be on vapor line because he has used dry at the outlet. If assume these words are not given, outlet of the compressor is not given, but you have to understand that if the inlet is wet, if you draw one vertical line, the point number 2 should reach to point number 2 should be on vapor line, or else he will mention the condition, So this not will be used many times, but 99% this condition will be used. 90% this condition will be used. Okay, next, remaining process is same. There is no change in the remaining process. Try to draw same diagram of the remaining processes. 1 to 2, 2 to 3, 3 to 4, like this. Okay, now I will make one more condition. Case number 3. What is the condition I will draw? Condition, the refrigerant R12 or R22, whatever may be, at inlet, not inlet, I will change now. At outlet of compressor is superheated. Outlet of compressor is superheated and inlet of compressor is dry. At inlet of the compressor is dry, outlet of compressor it is superheated. Then how to draw the TS diagram? Okay, you can try in your notebook how to draw the TS diagram for this. This is T, this is temperature versus entropy. Now, this is liquid line, this is vapor line. So at inlet of the compressor, it is dry. So point number 1 should be on this dry line, that is vapor line. So I have to locate point number 1 here. Okay, and outlet is superheated. So I have to draw 100%, I have to represent vertical line. There is no other option because 1 to 2 process is always isentropic process. You must represent vertical line. So start point is 1, end point is here somewhere. You locate up to this point. This is point 2. Now the question is how to draw the condenser part. So from here you draw one downward inclined line. From here you draw one constant temperature condenser. Again the process is remains same like this. Okay, this is one type of condition. Understood? So this is third condition. So only these 3 conditions will be given in the numericals. Okay, and 99% he will 90% to 99% he will mention only the condition either at inlet or at outlet. If they are not mentioned at inlet and outlet, it is not possible to solve the numerical. You have to assume whatever the condition you require and you solve. But 100% either you will give inlet or outlet. If the condition of the refrigerant at the compressor inlet is dry, 100% at the outlet it should be superheated. Keep in mind, this is a hint I am going to give. What is a hint? Inlet of the compressor, if the refrigerant is in dry condition, outlet it should be in superheated. Second condition hint is if the inlet of the refrigerant is wet at compressor, inlet to the compressor, the refrigerant is at wet condition, there may be two, and outlet of compressor, it should be dry. 90% you will give any one condition, either this or this. Okay, so we will solve one numerical, simple numerical, what we have solved in the previous class, same numerical, same data. We will solve one numerical. Okay, so let me take one numerical. Okay, a vapor compression refrigerator, so VCR, okay, of 10 tons. How many tons? 10 TOR. TOR means 10 tons. This is a unit of refrigeration. Capacity using Freon 12. So what type of refrigerant they are using in the given numerical? Freon 12. So in the thermodynamic data handbook, go to contents, first page, contents. There you will find Freon 12, properties of Freon 12. Okay. Then you will take some properties. That what are the properties required? We will explain here. Not to worry about it. Next. As the refrigerant has a evaporator temperature. Evaporator means the low temperature. Low temperature is minus 10 degrees Celsius. So I will write here evaporator temperature is equal to minus 10 degrees Celsius. And condenser temperature is 30 degrees Celsius. Condenser temperature will be always greater than evaporator temperature. 30 degrees Celsius. Okay. Next is assuming simple dry saturation cycle. In the previous numerical we have solved with superheated. Here it is dry. What is dry saturation cycle? Is the inlet or input of the compressor is wet. Keep in mind this condition. Dry means outlet of the compressor is dry refrigerant. Outlet of the compressor is dry refrigerant. And when you are considering outlet of the compressor is dry, obviously the inlet or input to the compressor should be in the wet condition. Okay, I will draw the TS diagram, not to worry. Input condition is wet, where? With respect to compressor, always with respect to compressor, keep in mind. Output is dry. And calculate COP, mass flow rate and power output. So we'll calculate COP, mass flow rate and power input to, always power input to the compressor. Keep in mind, always input to the compressor. So I will draw the TS diagram for this. What is the condition he has given? Dry saturation cycle. Dry saturation cycle. So I will draw TS diagram. Then I will draw the pH diagram once again. So this is saturated liquid line. This is saturated vapor line. So it is not like that. Sorry. I will draw it. Okay. Let me take pen. Here. This is saturated vapor line. Now, what is the condition he has given? Dry saturation line. Dry saturation line, nothing but keep in mind output or outlet of at compressor is dry. Means input is point number 1, output is point number 2 in the compressor. Okay, output point is dry. Where should I locate the point number 2? Point number 2 I should be located on dry. I should stop here. This is point number 2. Where should I draw point number 1? Always 1 to 2 is vertical line. So point number 2 will 100% it will come in the wet region, because point number 2 is only dry. So it is 1 to 2. For example, if it is for superheated condition, what will give you the word? Superheated. Dry will not use the word dry. Superheated cycle. superheated cycle. Superheated cycle means point number 2 should be in the superheated region. So how the TS diagram will be? TS diagram, it looks like this is saturated liquid line, saturated vapor line, and point number 2 is superheated. I am assuming that if the case is like that, superheated, then point number 2 will be somewhere here. So this is point number 2, and 1 to 2 is always vertical line. You have to draw one vertical line, and it will stop at here. Now you can ask a question, sir, condition may be dry or may be wet. Very good. If the condition is wet given, you take this point. If the condition is dry, you can stop here only. Okay, this condition will be mentioned in the given numerical. Don't worry. So here he has mentioned only dry. So point number 2 is dry, and 100% point number 1 will be in wet condition only. So what is the same remaining? Point number 2 to 3 and 3 to 4 like this, and 4 to 1. Okay, this is a TS diagram. And how we should draw PV diagram? Not PV diagram, pH diagram. In the refrigerant, we'll draw the pH diagram. Why you are plotting pH diagram? Because here there is a change in phase of the working substance. If the working substance wherever changes, we'll draw pH or TH diagram. pH. Okay. Same again, you draw saturated liquid line. This is saturated liquid. This is saturated vapor. Point number 2 should be on saturated, that is dry. Dry means nothing but saturated. Keep in mind. So point number 2 should be on this line. This is condenser B to C. C to, not, I will write it as 2. Point number 2. This is point number 3. And 3 to 4 is expansion process. During expansion process, enthalpy remains constant. So I should draw one vertical line. So here H3 is equal to H4. Now compressor part is, I have to draw one inclined line. So this is point. If the point number 2 is a dry condition, of course 100% the point number 1 will be at wet, because I cannot draw only small length. No, I cannot draw like this. I cannot draw 1 to 2 process like this. It should be vertical line. If the point number 2 is here, you draw one vertical line and show the upward arrow. So point number 1 will be in 100%, it will be in wet region. Okay. So this is a condition. What he has asked? COP he has asked. Simple formula you remember. COP is equal to refrigerating effect divided by work done on the compressor. Refrigerating effect is 4 to 1 process. This is called refrigerating effect. 4 to 1 is refrigerating effect. And here 4 to 1 on the pH diagram, here it is there. Point number 1 and point number 4. Refrigerating effect is a difference in enthalpy at first point and minus enthalpy at fourth point. H1 minus H4. H1 minus H4 divided by work done on the compressor. Out of these 4 process, 1 to 2 is compression. So you draw 1 to 2. So 1 to 2 is compression, means enthalpy at first point and enthalpy at second point, you need to note down. So which point enthalpy is highest? Enthalpy at second point is highest because it is x-axis. Okay. For example, enthalpy at point number 2 is more, but pressure at point number 2 is more than pressure at point number 1, because here it is on y-axis. On the x-axis, H1 is less, H2 is more. So you write H2 minus H1. So this is the formula. Now, my dear students, I will give a hint how to solve this numerical. I will not write all the values. Okay. First, try to find out all these 4 enthalpies. H1, H4 and H2. H4 and H1 both are in wet condition, so it will be very difficult. So in place of H4, I can calculate H3 because H3 is equal to H4. Enthalpy at 3 is equal to enthalpy 4 because it is vertical line. So in place of H4, I will write H3 like this. I will draw like this, H1 and H3. So here, so what is H1? We'll find out later. H1 is in wet condition. H1 formula, HF plus X into HFG. So why you are writing this equation is point number 1 is between saturated liquid line, saturated vapor line. So you have to write the formula like this. If the point number 1 is on dry line, directly I can write H1 is equal to Hg. If the point number 1 is on this liquid line, I could have written H1 is equal to HF directly. But it is between these two. Okay. So what you need to do is first calculate H2, my dear students. H2, I will tell you how to calculate H2. H2 is on dry line. What is the 2 to 3 process? Condenser. This is condenser. This is evaporator. Condenser temperature is how much he has given? Condenser temperature is 30 degrees Celsius. And evaporator temperature is minus 10 degrees Celsius. Okay. So go to 30 degrees Celsius in the contents in the Freon 12 thermodynamic data handbook. Go to page number Freon 12. There go to 30 degrees Celsius and note down the value of H2. And how to take these values already we discussed in the previous classes. I told you how to refer the thermodynamic data handbook. So at 30 degrees Celsius, the value of 0.2 means the enthalpy at 0.2, I will get dry condition. Here 199.47 you will get. 199.47 joule per kg Kelvin. If you are confusion with some numericals, again we will take one more classes and we will explain. Don't worry. Okay. For time being, for the exams, you understand how to take the value of H2. First point, go to contents. In the content space, they have given properties of saturated Freon 12 because the given refrigerant is Freon 12. In that, they have given the page number. Go to that page number. And here, there we will get first column temperatures. There, go to 30 degrees Celsius value. At 30 degrees Celsius row, note down the value of Hg. Hg. Why you are writing H2 is equal to Hg? Because point number 2 is on dry line. So 199.44 or 4743, whatever may be the value, you write. Similarly, point number 3 is also related to condenser. Point number 3 is also related to condenser here. So condenser temperature is 30 degrees Celsius. Same 30 degrees Celsius row, instead of Hg, now you need to take HF because point 3 is on liquid line. F stands for liquid. G stands for dry. In between these two, it is HFG value. Okay. So 30 degrees Celsius at point number 3. Point number 3 is related to 30 degree. So HF value you need to write. H3 is equal to HF is equal to how much it will be? 64.53. 64.53 is the value. So H1 we have written. Not written, we have to calculate using this equation. Okay, we'll find out now. H4 is equal to H3. Yes, H3 is calculated, H2 is calculated. Now only unknown is H1 to calculate COP. So how to calculate H1 is simple diagram. H1 is equal to HF at 0.1 plus X HFG at 0.1. Point number 1 is related to evaporator because it is at low temperature. Evaporator temperature is minus 10 degrees Celsius. In the same steam table, in the same thermodynamic data handbook, for Freon 12, first column minus 10 degrees Celsius, note down the value of HF. Note down the value of HF. So for minus 10 degree, so 26.85 kilojoule per kg. Similarly, HFG, same minus 10 degrees Celsius column, note down the value of HFG because point number 1 is in wet condition. So HFG is 134.93. This is the value. I hope all of you are familiar with thermodynamic data handbook. Okay. If you are not familiar, you mention in the comments box. So we'll solve one more numericals with the thermodynamic data handbook. I will scan copy. I will do the scanning and I will bring here the soft copy and I will explain. Okay. So now HF is calculated. HFG also have calculated, but X we don't know. Again, we have to calculate X to find the value of H1. So to calculate X, you need to remember one more point. I will draw TS diagram here because again and again I have to use the TS diagram. So here point number 1 is here, point number 2 is on wet condition. Here it is 1. Point number 2 is on dry condition. This is the diagram. Okay. Now, yes, this is TS diagram. 1 to 2 is what type of compression? Isentropic compression. So isentropic compression is nothing but entropy remains constant. So during 1 to 2 process, entropy remains constant. During 3 to 4 process, enthalpy remains constant. I will write here 1 to 2, enthalpy is same. During 3 to 4, enthalpy is same. That is a difference here. Okay, so please remember this point. So what is the entropy at point number 1? S1. Entropy at point number 2? S2. So S1, hope you will write S1 again using the same equation. Dear students, I will write here. Keep in mind, yes, point number 1 is in wet condition. So it is mixture of or it is sum of these two values. Here it is point number 1. It should be at point number 1 is equal to point number 2 is on dry like this. Okay. Point number 1 is in wet. Point number 2 is in dry. So when it is on dry, you need to take only one value, that is SG. SG. But point number 2 is related to 30 degrees Celsius. Point number 1 is related to minus 10 degrees Celsius. So these two values you copy from minus 10 degrees Celsius table. And this value you could take from 30 degrees Celsius table. So at minus 10 degrees Celsius, again Freon 12, the value of SF, that is entropy at first point, is minus 10 is 0.108 plus X, I don't know. SFG is 0.593. This is the value is equal to SG. Do not take at minus 10 degree because point number 2 is related to condenser. Okay, point number 1 is related to evaporator. At 30 degrees Celsius, directly note down the value of SG. Not necessary to write like this equation because it is dry condition. If it is wet, we have to write like this condition, like this equation also. So at dry 30 degrees Celsius, the value of entropy is 684, that is 0.684. So using this equation, you can calculate X. Okay, calculate X. That X value, this X value, you have to substitute in enthalpy equation. Where is that enthalpy equation? Here is the enthalpy equation. Here. For this equation, you have calculated HF, HFG. Now also you have calculated X. You will get 0.9 Okay, after calculating this value, you will get here 0.97. Okay, similar kind of numerical I have solved in the previous class. Don't get confused with values. That was superheated condition. Here it is dry condition. That's it. So for this equation, I will write the enthalpy. Okay, enthalpy is equal to H1. HF1 is how much? Directly I will write 26.85 plus 0.97 multiplied by 156.2. So this value will be 178.36. So I use a COP now. COP is H1 minus H3 divided by work done on the compressor is H2 minus H1. So if you know all the values, substitute in the equation and calculate the SCOP. Second unknown is mass flow rate of fuel. What we need to calculate? The second unknown, mass flow rate. Okay, here the COP is, we have stopped here, no? H3 you have to write. H3 is 64.53 is a H3 value. That is what we have calculated in the previous step. Okay, next H2 is, how much is H2? 199.47. 47 minus H1 is 178.36. Okay. So COP I will get it as, after calculating this, I will get 5.3. Okay. Here, the next unknown is mass flow rate. Am I audible? Okay. So mass flow rate, what is the formula is? Remember this formula. Mass flow rate of the refrigerant is refrigerating capacity . Refrigerating capacity is equal to mass flow rate multiplied by refrigerating effect. This is the formula. So now the question is, what is refrigerating capacity? What is refrigerating capacity here? But in the given numerical, go to on the first page. He has given the refrigerating capacity is 10 tons. He has given us 10 tons. So 1 ton is 210 value. So 10 ton you have to find out. So I will find out here. Okay. So look at the board. So let me go to the last page. Last page here. Yes. Here I will take a new page. So in the given numerical, refrigerating capacity he has given as, refrigerating capacity is 10 tons he has given. 10 tons. 1 ton is how much? 1 ton is 210 kilojoule per minute. So for 10 tons, how much is the value? So 10 into 210 will be the value of this refrigerating capacity. So refrigerating capacity is 2100 kilojoule per minute in this equation. So left hand side you have calculated now refrigerating capacity. Mass flow rate is unknown. I need to calculate refrigerating effect. So refrigerating effect, keep in mind, that is related to evaporator. That is related to evaporator. So in the TS diagram, if you take H1 and H4, H1 minus H4 is refrigerating effect. Okay. So in the pH diagram also I will show you in the pH diagram how it looks here. Always refrigerating effect is nothing but amount of heat absorbed by the refrigerant. So 4 to 1, the process 4 to 1 is refrigerating effect. So H1 is greater than H4. So H4 is equal to H3. You can take H1 minus H3 as refrigerating effect, because we know H1 value also and H3 value also. H1 is here, already you have calculated this value, and H3 you have taken from the thermodynamic data handbook. That value already we have substituted here. 64.3 is H3 value. So that enthalpy at 3, okay, refrigerating effect is equal to H1 minus H3. So H1 is 178 something we got. That I will write as 178.36 minus, how much is the value of H3? H3 is 65 point something we got, 64. This is from thermodynamic data handbook. Okay. So refrigerating effect value is, I will do the calculator. So this value, okay, write down some here only. If you have a calculator with you, you calculate this value, or else directly I will substitute as refrigerating capacity is equal to mass flow rate multiplied by refrigerating effect. I need this value, mass flow rate. So refrigerating capacity divided by refrigerating effect. Refrigerating capacity is 2100. 2100 kilo. Kilo is there. Let me take in kilojoule per minute divided by refrigerating effect. If you have a calculator, you tell me the value of this, or else I will write here directly. I have a final answer with me. So 2100 divided by 178.36 minus 64.53. If you do the mass flow rate, you will get approximately, you will get it as 18.48. 18.48 kg per minute. And students, sometimes they may ask you to write this value in kg per second. In that case, what we need to do is 18.48 kg will be there in the numerator. Seconds is 1 minute is equal to 60 seconds. Just divide by 60, you will get the value in terms of kilowatt, not kilowatt, kg per second. Watt is joule per second is watt. Here it is kg per second. So let me put it in this same form, because in the question paper clearly he is mentioned that the mass flow rate should be in kg per minute. In the question paper clearly mentioned it should be in kilojoule, kg per minute, sorry, kg per minute. Next unknown is last unknown, power input. The power input is also easy. It depends on all of these values what you have calculated. Power input is equal to mass flow rate multiplied by work done on the compressor. Okay, mass flow rate is 18.48. Work done on the compressor is, what is the difference between enthalpy? Which enthalpy? Compressor is nothing but 1 to 2. 1 to 2. Work is done on the compressor. So H2 minus H1. So H1 value already you know. H2 value also you know. Substitute. H2 value is 199.47 minus H1 value is 178. That's what we have calculated. In the previous case, I think we have calculated H1 value. Yes, we have taken value of 178, means obviously you have calculated in the previous step. So Simplify this equation, and power input is equal to, write the formula, this formula in the calculator, and tell me the value. That is, I'm getting as, okay, some students they are replying, they are getting 6.54, correct. This is kilowatt. So this is the power. These are the three unknowns. Okay. This is complete solution of this numerical. If you have any doubts, you can ask me in the comment section. Okay, I will solve more number of numericals on these topics. Okay, so to solve numericals on these refrigerants, you need to remember the cases, whether input to the compressor is dry or wet, or outlet of the compressor is dry or wet. Okay, normal case, if the input to the compressor is wet condition, outlet will be at dry. If the input to the compressor is a dry condition, the output point, outlet of the compressor will be superheated region. Okay, so this is similar solutions also I have discussed here, cases also I have discussed. Please go through the videos once again, you'll understand better. Okay, so thank you so much, my dear students, for attending the class. Okay, take care, bye bye. I will send these notes